When we are talking about solubility, we are talking about solids dissociating into their ions, very much like we did in Chapter 4. These are our dissociation reactions, but now we are going to quantify, instead of just saying strong, weak, or non-electrolyte, we're going to quantify how much these things are soluble, and it depends on equilibrium. So the first thing we need to be able to do is write the balanced equations for each one of these reactions. And they're always going to be dissociation reactions. So we have aqueous barium, and then we have two hydroxides. So again, we need to watch out for the dissociation to see how many of each ion dissociate, because that affects the moles of the individual chemicals. With the lead carbonate, we've got one lead and one carbonate. These are all aqueous. So every equilibrium reaction, every dissociation is going to be written this way. The solid is a reactant. There's just, that should be an aqueous, sorry. The solid is the reactant, and it is breaking up into its ions. So the dissociation reactions we've actually done many times this year. We are just going to take it another step, and now we're going to look at the equilibrium expression for these things. So when we look at the equilibrium for the barium hydroxide, for example, we get an equilibrium expression. It's called a Ksp, and here we can see that is going to be barium 2+ times hydroxide 1- squared. Oh, can't get that in over there. Oh. Okay, and the reactants, since they're always solids, will never be part of the equilibrium expression. So our equilibrium expressions only deal with the product. Now that actually makes things a little bit harder when you read some of the problems, because they don't give you amounts. If you're trying to make product and you don't have any of it to begin with, they're not going to tell you how much solid you have, because it doesn't matter. As long as you have some solid present, this will be at equilibrium. So it's still there. We can still quantify it with stoichiometry and try to figure out how much we have. There's silver squared times the dichromate, or the chromate, CrO4-2. But none of these Ksp expressions actually depend on the amount of solid. As long as we have solid, we will get an equilibrium. So the Ksp, which is the solubility product for any dissociation reaction, calcium to the third and phosphate squared, just depends on the molarity of the products. So here we get one type of Ksp math problem. Silver sulfide has a solubility of 3.4 times 10 to the negative 17th, 25 degrees, which they all will be. Calculate Ksp. Okay, so our Ksp reaction, we have silver sulfide, solid, turning into 2 silvers and a sulfide, aqueous. And we're always going to get aqueous ions. The Ksp expression is going to be silver squared times sulfur, which I'll show in a moment. But here we've got our rice chart. So we're doing equilibrium. And since the solids don't matter, we're not really interested in that. There is still an x value here, -x. Sometimes that's important because we want to define solubility correctly, but it doesn't affect the equilibrium, even though it still is there and it is still changing by that x quantity. That's what we have. So we're getting plus 2x and plus x. So our silver molarity is 2x. Our sulfide molarity is x. Make this a little smaller. Our Ksp expression is going to be silver squared times sulfide. And if we plug those molarities in, we have 2x squared times x, which we know is 4x to the third. Okay, so now how do we solve this problem? Notice I haven't done any math yet. All of these things are true regardless of the problem that we've been given. Notice here how he says, in the problem it's giving us the solubility, 3.4 times 10 to the negative 17th. That is our x value. Solubility is x. Or, as you will, for whatever reason in the book, they define it, they change the x to an s, and they'll do ice charts with an s instead. But if we just plug that in over here, we get our solubility, we can get our Ksp. So there are two variables in this equation. We can either find if we have the solubility, we can calculate Ksp, or if we have the Ksp, we can solve for the solubility. But we can also do more. Let's go up to the ice chart. We can say, what is the sulfide? Well, that's the solubility. What is the silver? Silver is actually twice the solubility, so it's 2x. So you got to watch out for what is being asked for in all of these problems. In this particular case, we have the Ksp is going to be equal to 4x is 3.4 times 10 to the negative 17th to the third power. And that's going to come out to be 1.57 times 10 to the negative 49th, which is a very small Ksp. Now, notice we used to call silver compounds, especially silver solid salts, not soluble non-electrolytes. But with equilibrium, we kind of get this new idea. Nothing is really zero. There's always a little bit that can come off. You know, the solubility is 10 to the negative 17th power. That is a little bit. It is quantifiable. So that's kind of the idea here. We're taking these solids that are either marginally soluble or not soluble, and we're looking at, well, they're not actually zero. Let's figure out how much is actually there, versus the strong electrolytes that we know that are not equilibrium problems. They just dissociate 100%. Okay, here we have three very large problems. Calculate the solubility of each of the following in moles per liter and grams per liter. And solubility, of course, is our x value in these ice charts. So let's take a look at them one by one. Okay, first one is going to be nickel carbonate. So nickel carbonate, solid, is going to dissociate into a nickel, 2 plus carbonate, 2 minus. The ice charts are always going to be the same for here, X and X. So our Ksp, which is nickel times carbonate, becomes X times X. And if we plug the Ksp in for that, for the nickel carbonate, we will get 3.74 times 10 to the negative fourth molarity. That is the solubility, the X value for nickel carbonate. Now, if we wanted to take that and figure out how many grams per liter that is, we would say 3.74 times 10 to the negative fourth moles per liter, because that's a molarity. If we just need it in grams per liter, this is a molar mass problem. 118.7 grams of nickel carbonate is 1 mole of nickel carbonate. Then we are all of a sudden in grams per liter, and we will get 0.0444 grams per liter of nickel carbonate. Okay, so this is the solubility. We can go in and out of grams per liter and moles per liter as well. And then if we were to do barium phosphate, okay, it's going to dissociate into 3 bariums and 2 phosphates. Okay, we don't care about the barium or the solid. This is going to be plus 3x for the barium and plus 2x for the phosphate. You always want to watch out for the questions and what they're asking. When they ask you, if they ask you for the molarity of the barium, sometimes you solve for x and you feel really good about yourself, but that's not actually what they're asking you for. So if they ask you for the individual ion concentrations, you need to watch out which variables they are asking for. So Ksp is going to be 3x to the third power times 2x squared. Okay, so that is a lot to simplify. We've got 6.0, I think, times 10 to the negative 39th. That's our Ksp. Equals, and now we, fix all of that. We got 108 x to the 5th power when that's simplified. And our x value became, let's see, 8.89 times 10 to the negative 9th moles per liter. And then if we needed to convert that into grams per liter, we could take the molar mass, which is huge, 601.93 grams per mole. And we're doing this for the barium, the whole molecule, barium phosphate. So this is the solubility of the solid. Okay, so not individual ions. And that would give us 5.35 times 10 to the negative 6 grams per liter. Okay, so here's our grams per liter, and here is our moles per liter for the barium phosphate. Okay, there's one more. Everything is getting smaller and smaller up there. We've got the lead bromide. Okay, so the lead bromide solid gives me a lead 2 plus and 2 bromides, minus x. Let's remember that x is still there for the solid. PbBr2. Don't know why that's up there in the numerator. Plus x for the lead, plus 2x for the bromide. Ksp is going to be the lead times the bromide squared. Remember, if they ask for expressions, you still need to write the expression, which is just the molecules, not the x's. Okay, so that comes out to be x times 2x squared. And for the lead bromide, our x value, we plug in the Ksp. X comes out to be 0.0105 moles per liter. That's the molarity of the lead bromide. And if we want it in grams per liter, molar mass 367 grams per mole gets us 3.85 grams per liter. So this one's pretty high. This is definitely a more soluble salt. And it's a bromide, so we expect that. 3.85 grams per liter, or 0.0105 moles per liter. So we have our general Ksp expressions, and if we have Ksp, we can solve for the solubility in either of these cases. And if there's a different question, we could go into these ice charts and say, hey, what's the bromide? What's the lead? Or, what's the phosphate? What's the barium? We could ask for individual ions as well. There's a lot of ways to ask these questions. This question gets a little bit trickier. Which of the following compounds is the most soluble? You cannot just look at the Ksps like we did for acids and bases. Because in acids and bases, we could only do that because all the coefficients were 1-to-1. In this one, we have coefficients of 3s. This is a 1 phosphate. There's 2 silvers here to 1. Here's a silver chloride is 1-to-1. Those coefficients affect the equilibrium expression. So I cannot just say that, hey, 10 to the negative 10th is the most soluble. It's actually not. What we need to do here, if we're solving for solubility, we need to figure out which one is the most soluble by solving for X. So I'm going to simplify these. You can go through the ice charts and justify them. This Ksp, watch what happens, is going to be X squared. The silver chromate, Ksp, is going to be 2x squared for the silver and a chromate. Okay, so 2x squared is the silver, and the chromate is just an X. And the silver phosphate is going to give me 3x to the third times the phosphate, which is just X. So you can see here that these affect the solubilities differently. When we do this, we get 3 different X values. Let's solve for them. The silver chloride X value, 1.22 times 10 to the negative 5th. The silver chromate, 1.31 times 10 to the negative 4th. That's more soluble. These are molarities. And then the silver phosphate, 1.61 times 10 to the negative 5th. Okay, so here, the most soluble is actually the 10 to the negative 4th. And we can see here that the one that we looked at first that had the highest Ksp, 10 to the negative 10th, is actually the least soluble of the 3 salts. So we got to be careful here. Solubility depends on X, not the Ksp. Now, of course, there's a catch. These coefficients are all different, so we had to solve for the X values to standardize them. If all of the coefficients were the same, if they were all in a 1-to-1 ratio, it actually would be possible to make some direct comparisons. So if the coefficients are the same, their Ksp expressions will be the same mathematically, and you can compare them. But if the coefficients are different, you need to solve for the solubilities to make a valid comparison. So now we have the solubility of strontium fluoride, and we've got 3 different scenarios here. One of them is pure water, which is just a normal solubility problem. But then one of them says, okay, we have strontium nitrate. And you'll notice that strontium has a common ion here, strontium fluoride with strontium nitrate. So we already have a source of strontium to begin with. How does that affect the strontium fluoride? And then the third example is sodium fluoride. And you'll notice that the fluorides match here. That's our common ion. So if we already have a source of fluoride to begin with, how does that affect the solubility of the strontium fluoride? So let's work through each one of those. Okay. First, our Ksp for the strontium fluoride. without going through all of the ice chart, gives us x times 2x squared, and the solubility for that comes out to be 5.82 times 10 to the negative fourth molar. Okay, so it's a fluoride. It's pretty soluble. Okay, but now I actually need the ice chart here for the strontium nitrate. So if we had strontium fluoride dissociating into a strontium 2 plus ion and a fluoride ion, two fluoride ions, minus x, we still have that x there, although the solid does not affect the equilibrium Ksp equation. We no longer have zero fluoride. We have no fluorine to begin with, but the strontium, we no longer have zero. It's 0.1. We have an external source from the strontium nitrate. The nitrate is a spectator. There's nothing in common with the nitrate, but this 0.1 strontium is a source of strontium to begin with, and that affects my equilibrium at the beginning. So when we add an x value to the strontium, we know that x values are not going to be significant if we have a common ion, and the only thing we have left here is the fluoride. So our Ksp equation becomes strontium still, because the expression doesn't change, it's still strontium times fluoride squared, and the fluoride becomes 2x squared. Okay, so the solubility is the x value, that's the strontium fluoride, that's the x value. The strontium is 0.1, the fluoride is 2x, the solubility is x. So you got to watch out for what is being asked for. When you solve for x in this case, you get 4.44 times 10 to the negative fifth molarity. So the molarity went down by a factor of 10 about. We had 10 to the negative fourth, now we're at 10 to the negative fifth. Okay. And if we do that again with the sodium fluoride, with my strontium fluoride, solid, turning into, lower this a little bit, strontium 2 plus and 2 F minuses. We have minus x for the strontium, even though that doesn't affect the equilibrium, that x still exists. This time we have no strontium, but we have a common fluoride of 0.4. Okay, so the sodium is a spectator, but my 0.4 fluoride comes down here is the beginning. That's going to make my x value, or rather my 2x value, negligible. So the fluoride is now 0.4 at equilibrium. My strontium is x. Neither of those affect the Ksp expression. The Ksp expression is still strontium, which is x, times fluoride squared. Fluoride now is just 0.4 because we have a common ion, so fluoride squared. When you plug that in, our x value now is 4.94 times 10 to the negative ninth molarity. Look at what just happened here. That solubility went down by a lot, quite a lot. By a factor of 10,000. Okay, why is that? Oh, this isn't going to let me, it's not going to cooperate. That did not stay together. Okay. The solubility went down by a factor of 10,000. And we can see why if we look at the common ions. Okay, the strontium common ion and the fluoride common ion are different in the strontium fluoride based on their coefficients. This is a 1:2 ratio up here. So because fluoride has a coefficient of 2, and my Ksp expression is going to be strontium 2 plus times fluoride squared. Because fluoride is squared, the fluoride is going to have a greater effect on the solubility. That was supposed to be a highlighter. Okay, the fluoride is going to have a greater effect on the solubility. So we see here, not only can we calculate the solubility with different common ions, but we can see which common ions have a bigger effect on the solubility. Normal strontium fluoride is 10 to the negative fourth. A strontium ion lowers it by a factor of 10, but the fluoride common ion lowers it by a factor of like 10,000 or 100,000 from the original. So it's quite a bit, or 1,000 or 10,000 from the original, but it's quite a bit from difference between the strontium and the fluoride, and that's because the fluoride has a squared relationship to the Ksp. So if you're looking for common ions to see which one will lessen the solubility more, it's the one that has a higher coefficient will affect the solubility the most. Here we get a very similar equation, but we can have common ions with water, okay? Hydroxides do this a lot. Textbooks love this. AP, mixed feelings about it. But watch what happens. Because my Ksp expression, we're not going to go all the way through this one here. My Ksp expression has a hydroxide in it. When we do an ice chart, hydroxides always do this with water. We can't just say it's 0 and 0, because that's actually not true in water with a hydroxide. In pure water, we know that a hydroxide is there at 10 to the negative 7th power. So this messes with the solubility of hydroxides quite a bit. And we can see that this is 10 to the negative 43rd, that 10 to the negative 7th for any hydroxide that's not sodium or potassium, generally this comes into effect a little bit. So we could calculate this common ion question with that hydroxide there as well. With a pH of 12, we would just say this common ion of the hydroxide, since the pOH is 2, the hydroxide is then a common ion of 0.01 molar. So that gives us the pHs can give us a different hydroxide molarity. So we could solve that problem as well. And then the third example, how would the solubility of a change in an acidic solution? This is less of a solubility math problem and more of a Le Chatelier problem. Okay? We know in an acidic solution we have hydrogens, and a hydrogen ion will react with a hydroxide ion. So saying that we have an acidic solution for a hydroxide is a way to say we are removing hydroxide product. This will make it more soluble. We will shift left, or shift right, because we're reacting with the product. Okay, and since my solid is on the left, shifting left and shifting right now has a meaning for the solid. A shift right means more of it dissolves. A shift left means less of it dissolves. A shift left can also mean we make a solid. So sometimes we'll say we'll form a precipitate. So this is just kind of the start of the next lesson, but we're going to look at how Le Chatelier can help us describe what's happening in the system too, if we are moving right or left, dissolving the solid or making a solid.